Okay, welcome everybody to this webinar for the practitioners in analytics. So in this series, we ask speakers to talk about developments in analytics that are also important for practitioners. And we think that conic optimization is also one of the big developments that are also important for practitioners. So it's really a great pleasure for me to introduce the speaker, Erling Andersen from Mosek. He is CEO of Mosek and also chief scientist. And well, I still remember that I think 1 year ago, or maybe 1.5 years ago, he also gave a presentation on this in Tilburg, the university where I was at that time. And that was very inspiring and also led to, I think, to applications of conic optimization and to papers. I also would like to mention the cookbook. Maybe he will also mention it. Mosek cookbook. That's about the modeling on conic optimization modeling, and I really like that cookbook. So this is also an advertisement for that cookbook. Okay, Erling. So the floor is yours. Oh yeah, maybe. I forgot to say that if you have questions, please ask them via the Q&A. I will keep an eye on that. And then I think halfway or sometimes maybe even in between, I will ask Erling the questions. So the floor is yours, Erling.
Thanks a lot, and thanks for the nice introduction. And I'm looking forward to talk about my favorite topic in optimization, which is conic optimization. And I've, in fact, I started sort of my work on conic optimization when I had a postdoc in Delft in the Netherlands with Dick's former advisors, Kees Roos and Thomas Chalerki. So that is something I spent something like 12 years on now. Okay, so here is an outline of what I'm going to talk about today. First, a small introduction, and then the main part of the talk will be conic optimization. Then there will be some benchmark results where I hope to prove to you that conic optimization is also relevant from a practical point of view, and then a summary at the end. Okay, so this talk is essentially about optimization. So here on this slide, I've put the generic optimization problem. So that is minimizing some function over some decision variables x. And the decision variables has to belong to some set of feasible solution, so capital X. So this problem could, for example, represent minimizing cost subject to various constraints on resources and so forth and so on. So this problem is very general. So a lot of problems in operations research, economics, and all sorts of areas can be formulated like this. But the problem is, the issue is that this problem is very difficult to solve because it's so general. And I would kind of say that this problem is so generic that it's not really useful because we can only solve small instances if we want to specify it on that form. Okay, so here there's another problem that probably most of you have seen before. That is a linear programming problem where we are minimizing a linear function CTX subject to some linear equalities and some linear inequalities x greater than equals 0. So here we have a very explicit structure. That is, all functions that goes into this optimization problem is linear. And the data for this problem is very simple because it's just one matrix A, a vector C, and a vector B. And of course, this kind of problem, we have very powerful algorithms, so we can solve them using the simplex algorithm or interior point methods. So we can solve problems up to a million of variables using standard hardware and software. And we know that this problem is convex, so all local optimas we obtain to this problem is also global optima. And in fact, this optimality of the solution we can very easily verify using duality. But of course, this problem has a restriction or limitation because we can't deal with nonlinearities. So out there in the real world, a linear model is fine in many cases, but of course there's cases where it's not sufficient, where we really have to deal with nonlinearities. So the main question that this presentation is focused about is there some kind of compromise problem class that allows some nonlinearities while keeping all the good properties of linear optimization? So can we relax the assumption about that the functions are linear a little bit and get some kind of class of nonlinear problems that we can solve efficiently? And perhaps not that surprisingly, given that this talk is about conic optimization, then the answer, at least my answer to that question, is a conic optimization problem is a sort of a good compromise. Is a very interesting special class of nonlinear models that are almost as easy as linear problems. Okay, so what is a conic optimization problem? Well, it has this form. So we are still minimizing a linear function. So basically, we now have, before we have a vector of decision variables, which was just one big vector. Now we think of this vector as a bunch of smaller vectors, okay? So the objective function is still a linear function. We have linear inequalities, and then we have our vector of decision variables. Each piece has to belong to a convex cone kk. Okay, so what we did here is that we kept the structure from the linear problem, except x greater than equals 0, we replaced by saying x has to be member of a convex cone. So kk is a non-empty pointed convex cone. So that means it must be convex, a convex set. So if you take any 2 points in the set, then the line between those 2 points is in the set. And it must have this conic structure. That is, if you take a point inside the cone and multiply that by any positive number, then it's also in the set. So clearly, x greater than equals 0 is a cone, because if you take any positive number, multiply it by a positive number, it's still positive. And then there's this pointed thing. Okay. Similar to the linear programming, we have a dual problem, and the dual problem is maximizing BTY. If you remember duality from linear programming, then you would also have BTY, and then in the linear programming case, you would have C minus ATY greater than equals 0. You almost have the same here, except that you don't have C minus ATY greater than equals 0, but it has to belong to the dual cone, and the dual cone is defined below. So we say KK star. And it's simple. So the dual cone is a set of is all those vectors that have positive inner product with all vectors in the primal cone. And for those who have some familiarity with linear optimization, you can almost see it's something like the duality gap has to be positive or something like that. Okay, so the dual problem, if you like, you can think about your primal problem as a dual. So whether you want to view things from the dual or the primal side doesn't matter. Both the primal and the dual problem are, of course, convex. And the objective sense is not that important. It's just flipping some signs if you want to minimize instead of maximizing in the dual. Yeah, so this is a primal. Here we just have x in kappa k. In the dual, we have a affine combination of the dual variables y in the cone. Okay. Yes. So what is the beauty of conic optimization? I think one of the nice things about conic optimization is that you get a separation of data and structure. So for instance, if you say you have a convex quadratic optimization problem, then, if you're minimizing f of x or something, you don't say anything about the structure. But here you have the data is the C vectors, the A matrices, and the B, and all the structure is in the cone. Whereas if you're thinking about an optimization in traditional functional form, you're minimizing f of x, and f of x includes both data and the structure. Okay. There's a very nice paper written by Arkady Nemirovsky on his website, and that reference will be at the end of the talk, which describes conic optimization and why it's important. And I will also go into why it's important on the next slide. And as you can see now, it's very similar to linear optimization. All what we do is that we replace x greater than equal with x in a cone. To some extent, that's not very interesting if we allow arbitrary cones. But, and this is one of the key points about conic optimization, we can, if we allow for only 5 different cones, the linear cone, the quadratic cone, the semi-definite cone, the exponential cone, and power cone. So 5 different cones I will show on the subsequent slides with a very specific structure. Then almost all convex optimization problems that appear in practice can be modeled using these 5 cones. Okay, so normally when you think about convex optimization, you're minimizing a convex function. This function could be anything, have all sorts of different structures. But this type of problem, if we reformulate it into a conic problem, using those 5 cones we have here, we can usually formulate it on conic form. So we are working, so we have something with a lot of structure and only very few items to work with, okay? And the evidence for this is, for instance, there is a library of mixed integer nonlinear optimization problems, and all the convex instances of those, they can be formulated using these 5 cones. There's also 2 discussion forums, CVX and CVX pi, where you're discussing how to use CVX pi. And you can only use CVX pi if you can formulate your problem using those 5 codes. And it turns out that in the majority of the cases where people ask, can my problem be reformulated into CVX pi form? Then the answer is yes, and then it can also be formulated on conic form. Okay, so what are those 5 cones? Well, the first cone is the linear cone, so it's just x greater than equals 0, so that's a cone. nothing new there. The next cone is the next cones is the quadratic cones. So the first cone KQ specified there. So what is that? Well, if you think about the quadratic cone in three dimension, this is exactly the ice cream cone. So if you buy an ice cream cone with 1 or 2 scoops and get it in cone, then that is specified by the first quadratic cone. And of course, there is generalized to arbitrary dimension. The second cone, or the one defined at the bottom, is called the rotating quadratic cone, and it's essentially an orthogonal transformation of the first cone. So in practice, it's sufficient that if we can model with one of them and solve problems with one of them, because you can easily translate from one to the other. It just turns out that in some cases it's nicer to work with the first cone when you're doing models, and in some cases it's nicer to work with the rotated quadratic cone. Okay, so let's see, how can we use the quadratic cone to model convex sets? So if we take a scalar x and a vector x and say t comma x has to belong to the quadratic cone, it's the same as saying t has to be greater than equal the 2 norm of x. So that means using the quadratic cone, we can model something with the 2 norm. Okay, let's try and take a half, so a fixed scalar number, comma t, comma v times transpose x in the quadratic cone. So that is equal to 2 times half times t has to be greater than equal the 2 norm of vtx squared. So you get the right-hand side there. So that essentially shows that using the rotated quadratic cone, we can easily model all sorts of convex quadratic term, because what we have on the right-hand side, t greater than equal x t v times vt times x, is a convex quadratic term. Okay. But the perhaps surprising part, if you haven't seen this before, is that if you have t greater than equal 1 over x and x has to be positive, then that's the same as saying x comma t comma square root 2 has to be in the three-dimensional rotated quadratic cone. So you wouldn't think that you could model something with x to the minus first with a quadratic cone, but that is in fact the case. If you want to model something with t greater than x raised to 3 over 2, then you can model that with the thing on the right-hand side, s comma t comma x. That is one three-dimensional vector and another three-dimensional vector in the rotated quadratic cone. I won't work out the details, but it's fairly easy to work out that these two sets are equivalent. Similar, t greater than equal 1 over x squared, comma x greater than equal 0. So it can be modeled with two rotated quadratic cones. Okay, so this is an example of some fairly simple sets that you can formulate with some quadratic or conic quadratic constraints. So we are saying all those sets or those sets, they are conic representable using the cones or using quadratic cones. Okay. Finally, let's take a look at the harmonic mean. So the harmonic mean is defined there. So t less than the harmonic mean on the right-hand side. Can we model that using conic? Is that conic quadratic representable? Yes, because if we introduce some variable set j and say set j comma xj comma t in a three-dimensional rotated quadratic cone for all j's, and then we sum up all the set j's and let them be equal to n times t divided over 2, then all these small quadratic rotated conic quadratic constraints and one linear inequality can be used to represent this fairly nonlinear set, the harmonic mean. I won't prove that, but I'll leave that as an exercise. Okay, let's try look at another example. So another thing that most of you probably have done is that you have a linear inequality at times x less than equal b, and what you normally assume is that the a vector is known and b vector, the scalar b is known. But in practice, you know, a may not be known exactly. There might be some uncertainty or something. So let's try to formulate a robust inequality saying now ATX has to be less than B, but A has to belong to some set, this set epsilon. And what is this set epsilon? Well, it's defined as some vector A bar times ht, h times y, and h is a matrix, and then there's some vector y, and the normal y has to be less than 1. So this is essentially a linear transformation of the unit ball, and the linear transformation of the unit ball is an ellipsoid. So this set epsilon, you can think of an ellipsoid. So essentially you want to have this inequality to hold for all A in the ellipsoid, okay? And using a little bit of math, you can rewrite that robust inequality into the inequality below. So A bar t times x plus norm ATY less than B. And so you can see that the norm of ATY is pushing the solution into the interior. So that means, you know, the optimal solution will be in the interior, and hence it will be robust, because even if sort of the real y is somewhat different from the bar A, then x will stay feasible. Okay? And this conic quadratic or this inequality is conic quadratic representable as shown with the last two with the linear equality and one conic quadratic inequality. So t comma hty, so you create one big vector with this, and that has to be in the quadratic cone. So conic optimization is very useful when you start working with robust optimization. Okay, then there's a cone, the semi-definite cone. So the semi-definite cone is a cone of all positive semi-definite matrices. So clearly, if you have a positive semi-definite matrix and multiplied by a positive number, it's still positive semi-definite, so that's clearly a cone. At least in theory, there's a lot of use for this cone because you can approximate a lot of non-convex problems, for instance, graph partitioning problems with the semi-definite cone. And there's something, if you want to find the nearest correlation matrix, you also get into semi-definite optimization. I will not talk further about this cone because I think the two other cones that I have on the next slides to some extent is more interesting. But from a theoretical point, the semi-definite cone might be the most interesting, but it might, because solving big problems over the semi-definite cone is quite computationally expensive, so it might be less interesting in practice. Okay, so the linear cone, the quadratic cone, and the semi-definite cone belongs to the class of symmetric cones. And the definition of symmetric cones is that they are self-dual, and then they have a property that they are homogeneous. it turns out among all the cones that you can think about, there's only 5 cones that are symmetric. Okay, so we have seen 3 of the cones. The other symmetric cones that I haven't covered is the positive semi-definite cone of Hermitian matrices where other complex or quaternion entries and some highly esoteric matrix, 3 by 3 matrix. Okay. So it turns another thing that holds for symmetric cones is that they are very closely related to Georgian algebra. And so, you know, we all know that we have, okay, so we have linear problems, we have convex problems, and we have non-convex problems. And we all, of course, know when we move from convex problems to non-convex problems, the problems get much harder. But inside the class of convex problems, or at least conic optimization, the problems defined only with symmetric cones forms a special class of conic problems that are easier to solve than when you move to other cones outside the symmetric cones. And of course, we call those cones that are not symmetric, we call those non-symmetric. Okay, what are the non-symmetric cones? Now I'm going to show you 2 non-symmetric cones. One is the power cone, and it's defined like this. So here we have the primal power cone. So for convenience, think about all the alphas as numbers between 0 and 1, and some of the alphas sum to 1. I wrote it a bit more general, but it's sufficient to think about the alphas as numbers between 0 and 1 summing to 1. Okay, so it's basically the product of some variables xk raised to alpha has to be greater than equal the 2 norm of the vector set. Okay, so what can we model with this? Let's assume alpha is between 0 and 1 and take t comma 1 comma x in the primal power cone alpha 1 minus alpha. So that's the same as saying t is greater than equal to the absolute value of 1 over alpha. So for instance, if you take alpha 1/3, then you can model the set x raised to a power 3, right? If we take x comma 1 comma t in the power cone, then you have x raised to alpha greater than equal t. So if once again, if you take alpha to 1 over 3, then you can model the set x raised to 1 over 3, right? So using the power cone, you can build conic representation of simple convex sets involving rational polynomials or of 1 variables. Okay, now let's look at the set. Now we have a vector x and a scalar t, and then we say that has to be in the power cone of all the alphas equal 1. So that is the same as saying the product of all the x's has to be raised to 1 over n greater than equal t. And what we have on the left-hand side on the equality is the geometric mean. So that means using the power cone, we can build models with the geometric mean. So why do I emphasize that? Because it's my experience that a lot of convex problems, they actually involve norms, so distances, or means. Sometimes it's a bit hidden, but in many cases, when you start looking and analyzing convex models, you end up with some mean and some distance. Okay, let's try to see another example. So let's assume that we have this convex function y raised to minus a half. So this is a convex function, and then you can do something like taking the perspective function of that, and you know the perspective function of a convex function is also convex. So the set there x times x divided by x in parentheses up the raised to minus half less than t, that's a convex set. So is that conic representable with the power cone? Yes, it is, because if we square on both sides, then we get, and we multiply by y, then we get x raised to the power 3 is less than t squared to the times y. Then if we raise to 1 over 3 on both sides, then you can see you have absolute value has to be less than t raised to 2 or 1 over third times y raised to the power 1 over third. And so that is essentially the power cone. And the right-hand side there on the power cone, we could write another way, t raised to 1 over third times t raised to 1 over third times y raised to 1 over third. So that is essentially the geometric mean on the right-hand side of t, y. Okay. So we had the primal power cone. So there's something called, of course, there's the dual power cone. And the dual power cone is defined this way. It's fairly rare that the dual power cone pops up in practice. In fact, I know only one application, and that is if you work with the sum of non-negative circular polynomials. But one important thing is, if you redefine the inner product, then the power cone is self-dual, but it's not homogeneous, and hence the power cone is not symmetric in general. Okay. Next, the next cone we are going to discuss, and the final cone is the exponential cone. So the exponential function is e raised to some variable, in this case x3. And let's take the exponential, the perspective function of the exponential function. So it's x2 raised to x3 divided by x2. Then we know that this is a convex function for all x2's greater than or equal 0. And then we use this to define the power cone. No, the exponential cone, sorry. So the exponential cone is 3-dimensional. So you have x1, x2, x3. So x1 has to be greater than or equal x2 raised, x2 times e raised to x3 divided by x2, and x2 has to be strictly greater than 0. And by the way, I forgot to show that the power cone is actually a cone, but it is. But here you can see that the exponential cone is really a cone, because if you multiply x1 by alpha, x2 by alpha, and x3 by alpha, you get alpha times x2 is greater than or equal alpha times x2, and then the alpha cancel out in the exponent. Okay, and so then you have this, so the main part of the exponential cone is the thing with the e, and then you have the second part, and this is sort of the case where x2 is equal to 0. It's just to make sure that the exponential cone is a closed set. Okay, so what can we model with the exponential cone? Yes, let's take t, 1, x in the exponential cone. That's the same as saying t greater than or equal e raised to a power x. So that means that we can using the exponential cone, we can model convex sets involving e to the x. If you say x comma 1 comma t and the exponential cone, that's the same as saying t less than equal logarithm of x. So once again, we can build convex model. We can convex model involving logarithm of x. We can make a conic representable using the exponential cone. If you say 1 comma x comma t in the exponential cone, then you get this entropy term. And if you say y comma x comma minus t in the exponential cone, you can model with something known as the relative entropy terms. So using the primal exponential cone, we can model quite a lot of different convex set with the exponential function and the logarithmic function. Now, let's just try show how does it work with one example. Let's assume we want to compute the analytic center of a polytope. So that corresponds to maximizing the sum of the logarithm of xj equal to where we subject to the constraint ax equal b, x greater than equal 0. So this is conic representable as follows. So you're maximizing sum of some variables tj, ax equal b, and then you say xj comma 1 comma tj in the exponential cone for all j. Okay, so let's see. Yes, if you want to compute the logarithm of sum of e raised to xk less than t, then you can compute that. Then it's also conic representable as follows. So you introduce some variables set j comma 1 comma xj minus t in the exponential cone for all j's, and you add this linear inequality. So the first nonlinear inequality is conic representable using the last two constraints. Okay, this one I will not cover. You can by what is known as geometric programming. You may have heard of that. About that, you can represent with the exponential cone. Here's a dual exponential cone. So the exponential cone is not self-dual, and therefore it's not a symmetric cone. So there are things like the convex function there that are not representable using those 5 cones. So the claim is the linear cone, the quadratic cone, the semi-definite cone, the power cone, the exponential cone can represent most convex optimization problems that appears in the practice. But there are nevertheless some convex sets that are not representable using those 5 cones, and this is one example. But of course, you can imagine that in the future that we expand the number of cones that we can deal with, and then we could handle this set. Or we may discover a way to formulate this convex function there using the cones that we already know. Okay, so on the subsequent slide, then here we have the primal problem, we have the dual problem. The usual duality gap holds. So if you have a primal, if you have a primal feasible problem, or you have a primal feasible solution to the, or you have a feasible solution to the primal problem, you have a feasible solution to the dual problem, then the dual, the primal objective minus the dual objective is positive. And that means if the duality gap is 0, you have an optimal solution. And for linear programming, we know if there's an optimal solution, there's always a dual solution that helps us verify that the primal solution is optimal because there's 0 duality gap. This also holds almost in the Conic case, but there are cases where it doesn't hold. So there are some tricky cases. And one example is if you minimize x raised to, if you minimize 1 over x greater than or equal to 0, then you can see that the optimal value is 0, but it's never attained because x has to go to infinity. Similar at the last example on this slide, in order to find a feasible solution, you have to take x to plus infinity. So the duality theory you know in the linear case almost holds in the conic case, but there are some tricky cases. So I won't cover that. I think, well, yeah, I think I will stop here. So I talked with Dick about that there should be some time for questions after the first part. So I will stop here and then show the benchmark results after the questions.
Okay, so I don't see any questions in the Q&A, but maybe there are questions.
Can I ask a question?
Yeah, of course, Dimitri.
Yeah, Erling, in your experience, has there been any interesting practical problem that you cannot put formulated in the 5 cones that you presented? These are not academic examples. I'm talking about the real world examples.
Yes, in fact, the first function you have up there is the logarithmic mean of temperature difference. That is not a convex function, but if you're looking at the inverse of that function, then that is convex. And you can go to we have a blog post about this, and this pops up in practice. So, so there are some, when you design some equipment that I cannot remember exactly now, then this pops up.
But you say maybe it might be representable. We actually do not know 100%. We haven't found the representation.
You know, because, you know, it's like Farkas' lemma. It's very easy to prove that it's conic representable, but it's hard to prove. It's much harder to prove that it's not conic representable using the 5 cones, because how do you give a certificate for that? And that's something we have been thinking about, but we don't know what the answer is to that question.
Great, thank you.
Erling, there's also another question now. Can you suggest a good textbook to learn conic optimization?
So what is a good textbook?
I think maybe by Nemirovsky and Bental.
Yeah, so, but okay, yeah. So the book by Nemirovsky and Bental will cover all the symmetric cones, but the non-symmetric cones is something that is fairly new. So Lieven Vandenberg, he has some very nice slides. Well, he covers that. So the modeling cookbook that we have, it's sort of an much extended version of these slides discussing what can you model on using these 5 cones. Yeah, I think that is probably the best one. I remember Leo Liberti. He's writing a book in optimization. It's not complete yet, but there's a PDF version on his website, and that might be nice too. But it might also cover other topics in optimization.
Yeah. Okay, but if you look at the website and cookbook Mosek, then you will find that that's very nice treatment of conic optimization by Mosek. Thank you, Anne. Please go ahead.
Okay, so so optimizing over linear and quadratic cones, I think all the major commercial software that you know about, so our competitor Ruby, Cblades, FICO, NAG, probably also SAS, they will solve these kind of problems. When you move beyond the quadratic cone for semi-definite optimization and the non-symmetric cones, there's much less software. So of course, I think the most complete software I would say is Mosek. We deal with all these 5 cones, and you can also have integer variables. And now I'll try to convince you that we can solve large instances of these conic optimization problems using Mosek. Okay, so the hardware I'm using is a fairly recent AMD-based server, so it's specified there. I use Mosek version 9.2.30. I use 8 threads. All times that you're seeing is in wall clock sections. It's in wall clock seconds. And the test problem I've chosen, I picked some from the public benchmark library, CBlib, and some problems that we have gotten from customers. And the first problems here are all, they involve only the linear cone and the quadratic cone. And the first column shows the number of rows in the A matrix. The second column shows the number of conic quadratic constraints, and then the number of variables and the number of matrix variables. So there's no matrix variables, so these are not semi-definite optimization problems. So you can see the number of rows in the A matrix goes up to 2.5 million, and you have up to maybe 2.5 million conic quadratic constraints. So that would be about 2.5 million nonlinear inequalities if you think about traditional optimization, and then up to 8.5 million variables. And so the problems represent structural engineering, some filter design, and so they come from different areas. Yes, some limit analysis. Yeah. So they represent different application areas. So here you can see the primal objective for all these problems, the number of figures that we estimate that are correct in the primal objective value. So it's from 7 and up to 12. We would sort of, the industry standard is to ask for about 8 figures of accuracy in the objective value, and we get that in almost all cases. So the interior point algorithm that solves these problems requires from 0, because the problem was solved in pre-solve, so up to about 40 iterations. And the time to solve these problems is from anywhere from 0 seconds up to, I think, 120 seconds. So this is about 2 minutes. So even if these problems are quite nonlinear in the sense that there are a lot of sort of conic quadratic constraints, we can solve them in from a few seconds up to 2 minutes. And so this is quite fast. For instance, those problems called MQL 180 and QSSP 180, So in the early 90s, those problems take now about 10 to 20 seconds. In the early 90s, you needed a supercomputer taking up a big room that was water cooled in order to solve these problems. Now you can solve them on your laptop in virtually no time. Okay, so problems involving quadratic cones, you can solve them quite quickly. So now let's look at problems that involves the exponential cone and the power cone. And I use the same hardware as before, 8 threads. So it's running in parallel, times in the wall clock seconds. And benchmark is from this public library of benchmark problems and customer supplied. And so here are the problems. So the biggest problem has maybe about 2 million rows in the A matrix and 6.5 million variables. And there are about up to something like 1.3 conic constraints. So that would mean probably in the first example there is 1.3 million three-dimensional power cone constraints. Okay. Once again, these represent various application areas, something like robust optimization, logistic regression, entropy optimization, yeah. So let's try and look at the results. Once again, here's a primal objective, the number of significant figures, the number of interior point iterations, and the time to solve the problems in seconds. So you can see these problems are a bit harder to solve. We don't get 8 figures of accuracy in all the problems, but in the worst case, we get about 6 figures of accuracy in the objective value. So this is quite good. The number of iterations can be quite a bit higher here. There's one taking 212 iterations. So these problems are indeed harder. And time is also a bit higher, up to something like 10, 15 minutes, right? 700 seconds. But a lot of them also solves in a very low amount of time. So even though these to some extent they are not non-convex problems, but they're in a way quite nonlinear problems, and even non-smooth on the boundary because they involve something like logarithm or something like that, then we can solve them quite quickly.
So Erling, 5 minutes left, yeah.
Yeah. So here's the summary. So conic modeling using the linear, the quadratic cone, semi-definite cone, and power cone, and exponential cone, we call at Mosek extremely disciplined optimizations, like extremely disciplined modeling. And the nice thing about doing this kind of building model this way is that you know your model is convex, and there's a very good chance that you can solve your model quickly. You might add more cones in the future. And of course, the term extremely disciplined modeling is inspired by disciplined modeling by Michael Grant, Boyd, and Yi. So this is the thing that is behind CBXPy. And so these models can be solved efficiently using a primal dual interior point method. Yeah, so I didn't have time to talk about that. And it preserves all the good properties of linear optimization. It's a very simple model. It has explicit data. Normally, when you have to do nonlinear models, you have to think about convexity. You have to think about gradients and Hessians. No need to think about that. Duality holds for conic models almost like for the linear case, almost. And as I mentioned, there's no issues with smoothness and differentiability. If you want more information, particular about Mosek, then there's a free trial and a free academic license on our website. And we solved linear and conic optimization, and it should say mixed integer problems. So you can have integer variables, except if you have a symmetry conic constraint. You can call Mosek from all sorts of interfaces like C, Java, Julia, MATLAB, R, Python, and more. There's documentation at this link, and you can get the cookbook that Dick mentioned, and there's also a modeling cheat sheet there. So normally I would bring some of the cookbook along and give it out, but that's not possible. But you can get a PDF version on this link. And there's a bunch of tutorials at our GitHub site with Python notebooks that shows how to build various conic models. Yes, and then the remaining slides are references. So I reached the end, and I thank everybody for the attention and listening.
Thank you very much, Erling, for this interesting talk. So I have a question here. Does the software convert to conical form automatically?
Only for quadratic problems. But you see, I would say this is, I know, everybody in this business, they would like to put some kind of hat on their head, and then the model goes automatically into the computer, right? Or even better, I just write down my model and then I convert it to conic form. But actually, I would argue this is really not such a good idea. And you should, in fact, be glad that it's not a good idea. Because what we are good at as analytics professional is building models. And if you just write a model down with f of x, g of x, and hope that the software will convert it in, you're, in many cases, not much work is left. But there's, in fact, an important role making sure that you have a good model. And typically, when a human is converting a problem into conic form, you can do much better than some automatic software, right? And in any case, there will never be a piece of software that will take an arbitrary model and convert it into conic form, because the first thing you would have to do is to prove your model is convex, and proving your model is convex is NP hard. Okay, so there's no, there's no way around, well, something like CBXPy can, if you write your model along the CBXPy rules, convert it into conic form. But there, and that in many cases works well, but I will claim doing this manual is normally, or at least in many cases, a better idea, because you will end up with a model that is better in the end.
Okay, thank you very much, Erling. Looking at the time, there were several more questions, but I think time is up now. So thank you very much, Erling, for this interesting talk. And the next webinar for analytics for practitioners will be in February. But if you have registered, then I will send you also information about it. So many thanks for your attendance, and see you hopefully next year in February. Many thanks, Erling.
Yeah, thanks.